Hey folks, Todd Coburn here with the Aerospace Structure Series. We're back to our Composite Structures playlist. Specifically, we're going to focus this time on bolted joints in sandwich structures. So let's first look at a typical sandwich structure. We just have it attached to something, some kind of plate where there's an external load being applied, as we see here. We can see that we have sandwich, we have a bolt, which looks like we just have a drill through the composite, which often happens, and we have some kind of plate or attaching member that could be composite or metallic or whatever, which has a shear force applied. Okay, this is a very common joint. And what we're going to have to do, we're going to find now, normally we found in our Structures 1 playlist that often if we have an eccentric joint, which is always, we're going to ignore the moment. And this works as long as the members are relatively thin. But as those members get thicker, that moment should not or could not be ignored. And since sandwich structures are typically thicker structures in order to get more efficient bending stiffness, we're generally going to have to evaluate how those loads enter and are reacted out in that joint. And while it's not completely challenging, it's a little more challenging than the average analyst is perhaps ready to deal with. Okay, so we now have this force applied, a shear force, and we got to think how this is reacted. Well, if you think back to our sandwich model, our core is relatively weak and non-stiff relative to the face sheets. And we assume that it takes shear, but really has no ability to carry this moment, or very little ability. But these face sheets are relatively stiff and strong, and since this hole goes through those face sheets, we can react out the moment that develops as a couple between the face sheets. So the upper and lower face sheets can carry that. In our model, we allow those face sheets to carry axial loads and shear in plane, and this is consistent with that model. So with this said, we're going to get a couple between our upper and lower face sheets. If we sum our moments about, say, the midplane of the lower face sheet, we find that that force times that distance to the force, which is the h, the distance between the centroid to the face sheets, plus half the extra thickness of the upper face sheet, plus half the plate thickness, minus the force times in the face sheet at that midplane times h is got to be equal to 0, right? Just basic statics. We can solve this and we find the relation for the upper cap or the other upper face sheet load. If we now sum our axial forces, we can find that the force in the lower cap is given by this. So this allows us to get our upper face sheet force and our lower face sheet force. And then we can evaluate with standard analysis whether or not that load can be reacted. Let's take a look at how that works. So we have already calculated what those face sheet loads are. Once we have those face sheet loads, the upper and lower ones that we just derived, we can now evaluate our bearing strength in the face sheet. That's just P over dt. And we can evaluate our margin of safety using that against the bearing allowable of that material. We can also assess our fastener. Remember, we have this force, and it doesn't magically get into these face sheets. This is going to introduce bending into our fastener. So if we just draw a little shear and moment diagram, and we'll draw this on edge. So from the midplane of the applying plate, the plate that's loaded, that's where that load is introduced. We have a constant shear until it's reacted in the upper face sheet, and then it's constant until it gets reacted down in the lower face sheet, which gives us this shear and moment diagram. The shear and moment diagram applies to the bolt itself. So in order for those two face sheets to take this load out, we're going to get this shear and moment diagram in the bolt, and now we can write an interaction equation to evaluate the bolt for that shear and moment. That is our shear stress in the bolt. That is our bending stress in the bolt. We can write the stress ratio on these two and then use the interaction equations using our methods from Structures 2 when we evaluated fasteners. So the next idea, now that we've evaluated the face sheets for bearing and the and the bolt itself for the bending that's developed. Let's say instead we have this external plate that's applied with say an axial load, a vertical load. Now we can see that this bolt is going to develop tension stress, P over A, and that's our standard thing. We're going to use that thread area of the bolt for that. We also are going to get, as that bolt is pulled upward by the upper plate, it's going to be resisted by that washer bearing against the sandwich. So we're going to get a bearing stress underneath that washer on the annulus of contact, which we can write that stress like this, which can be written against the bearing allowable of the face sheet as well, or compression if you want to be more conservative. And that also will end up propagating into a crush stress on the core. So if we assume that that force fans out at 45 degrees through the face sheet, that gives us a slightly larger area, and the effective diameter of that area bearing now on the core, so that we just evaluated the face sheet for crush, and now we have crush in the core, but the effective diameter fans out a little bit further through the face sheet. The thicker the face sheet is, the more that fans out. We can calculate the effective diameter this way, and then we can calculate the crush strength of the core. This is the crush stress, and evaluate that against the stabilized compression value of, if that's honeycomb, or just the compression through thickness compression value of the core material. We can write that P over pi d. So that is so we see the crush stress that we have here. We also have around the edge, if you look at this upper rightmost picture, around the edge as that bolt is pulled through and it's trying to drag the washer through the material, we develop a shear stress on the core. So if we just calculate the running load going around that area of contact, that's that D effective times pi, that's the distance around, and then the stress is just that divided by the thickness of the core. You could actually use H instead of the thickness of the core here. Would actually be even better. Okay. Now if we have a flanged insert extending through the sandwich, we basically are going to do the same thing. Instead of a washer on the bottom, we're going to have that D effective flange. And once again, this is our free body diagram of how that force is reacted out. Calculated exactly the same way as we just saw. Now let's take a look. Often what we'll do though is they will have inserts that don't all go all the way through. This is very common because it's very easy to install. What they will do is drill a hole in the sandwich through one face sheet and down into some depth, which now this is shown only going partially through the core, which is not very ideal. Sometimes they will go all the way to the lower face sheet, but not through the lower face sheet. That's a little better because now you're getting bonding action on the bottom of that insert against the face sheet itself. That is a little better. Going all the way through both face sheets is a much better load path. However, this is done all the time, and as structural analysts, we should be able to evaluate whether or not it's acceptable. Just because we don't like it or think there's a different way to do it does not mean it's not acceptable. We need to be able to differentiate between our opinion of what the best method of design is and whether or not our role is of figuring out whether or not this is acceptable for meeting requirements. So this is not as ideal, and it's going to introduce loads in the core in a way that the core is not intended to take, but we can still evaluate it, and here's how we would do it. So this will apply to any of those cases. You can see we have this face sheet. They've drilled through, and now what happens is we have this force acting on the plate. You can see it's reacted out by the upper face sheet, but it's not carried down to the lower face sheet. There's nothing but the core itself to carry that. So we're going to have a couple things. First we're going to do is we're going to take the shear out, going from that middle plane of the face sheet to the mid plane, from the mid plane of the plate that applies a load to the mid plane of the face sheet. Whatever that distance is causing a moment, and that moment has to come out. The force is going to be taken out in shear in that uppermost face sheet. But then we have this moment which still has to come out, and we can do that this way. Our eccentricity is that plate thickness over 2 plus the flange thickness plus that TU over 2. That's the eccentricity between there, and that's the moment that's being developed. And the shear is all going to come out that uppermost face sheet. Now, if we have other members, say washers or other things in here, that would be even less ideal. And if that's the case, you can just replace this T of the flange with the summation of all thicknesses of everything between those two plates, the applying load plate and the face sheet thickness. Okay? The moment is now going to be reacted as it's reacted. It no longer can be carried by the two face sheets because it's not carried down to the lower face sheet. So it comes out. You could just imagine that it's carried in the core out of plane. We're getting a couple like this. The moment is just PE. We calculated E already. If we think back to a thin line, this is not a half circle. This is a half circular line. The centroid of half circular line is 2r over pi. We saw that back in statics. Now we can idealize that moment is being reacted as a pair of shear forces centered at that. Here's another picture looking, a little sketch looking down on that area of contact. Remember, what we've got is a running load along one edge of the insert, the front edge, and a running load on the back, and they're going in opposite directions. In fact, this little picture here is going to help you visualize this. Is that moment is acting, it's reacted by a running load going around, a running load going down on this half, and a running load going up on this other half. Okay, and if you equate those two running loads as just two shear forces, then we see that those are spaced at y bar and y bar. So it's 2y bar, which is 4r over pi, is the eccentricity. I'm going to call that E sub s, between the centers of those two forces. So the force is just is calculated that way. So we can actually say, okay, the reacting shear force then is just that m over that eccentricity. The average shear stress then is roughly that force divided by its area. Now the area is just half of the area of a circle, right? The periphery of a circle, which is just pi r, which is pi d over 2, multiplied by what that h dimension is from the, and we can actually, you could use that from the center of the face sheet to the bottom of the insert, or from the bottom of the face sheet to the bottom of the insert, but actually using that hi that I'm showing you here, which is just from the top of the sandwich to the bottom of the insert, would be acceptable way to do that. That's our shear stress. We compare that against the shear strength of the core, which we can simplify to this way, where di is just the diameter of that insert that extends down into the core, not the outer diameter that's bonded up against the face sheet. This insert should really be wet installed with Dapco or some kind of adhesive that will flow and fully attach it on all surfaces, including to the face sheet and to the core, and everything else. Any voids in the core should be filled. Okay. Now, if we have a little partial insert subjected to tension, our running load that's reacting it around the outside of the insert is just P over pi di, with that same definition of di. The stress is just that ns divided by hi, which is the area of contact. If we were to subject the same partial insert, not through insert, to torsion, that torsion stress is going to be reacted by the core. Now, if your insert is bonded to the face sheet, you could react some of that against the face sheet as well. But if the insert is not completely bonded around, then the core will have to resist that, and you could just calculate your stress this way. Your shear force is just T over that over R, which is a D over 2. We could write NS is that S divided by pi D, and we could write our shear stress like this. You got that? So that's how we can assess partial or non-through inserts for tension and torsion. Okay? All right. Now, we also talked before about crush. We have to be careful when we're installing fasteners through sandwich. A lot of times the core material is so much less stiff and less strong that it can crush quite easily. So we have to be really careful to control torque. And unless you go out there and calculate specific nut factors for your sandwich structures, the nut factors you find in standard references are probably not going to be applicable to core, where the stiffness, the stiffness of the core is going to give you a completely different torque force relationship than you normally would get with a typical kind of fastener. I like to use snug plus 1/6 of a turn. Now this is not great for retaining fasteners, but all these fasteners through sandwich structure should be bonded, wet installed. So you butter up. I like to butter up the bolt and the threads and the both sides of the washer and underneath the head of the bolt and underneath the washer head. And when we put this together, that means that you're going to get not only mechanical locking but bonding as well. If you're snug plus 1/6, I found for soft cores like the row cells we were using on the Delta program, that seemed to work pretty well. Remember back, we studied in our Structures 2 playlist about how to evaluate tension, preloaded tension joints. The same principles apply here. I'm going to give you these equations kind of in a brief fashion for our sandwich structures. We're going to assume that load fans out 45 degrees, as is typical. You can see that here, that we're fanning out the load from the edge of the washer 45 degrees. That's going to give us a cone angle like this. Now, normally we're going to be fastening 2 or more members, but with bolts, sometimes we're going to be focused just here on this sandwich itself. So we can imagine the effective cylinder. We can basically assume that cylinder is actually, if you fan that out to the quarter point, right? This thing is the lower cone goes through half of the sandwich, and the upper cone does. The lower cone goes through half the sandwich. So if you come out to halfway of each, half of the half, that's h over 4. That's what we're going to assume that fans out to. If we use that as our effective diameter, we can calculate our assumed area of our cylinder and the stiffness of the member like this. We can then use that to evaluate what is the compression on the core for our turn, whatever our turn is, using the same approach that we learned before, remembering that the lead is the advance of the nut in one turn is just the pitch for a single threaded fastener, which means if NT is the number of turns, the deflection or the movement of the nut or of the bolt downward is going to be that number of turns times the lead, and we can then estimate how much force is applied using the same methods we did before, where like this. So this is the stress. This is the force, is Km that we just calculated, times that deflection in sub T times the pitch, and we can use that preload force to evaluate the crush of the core to make sure the core doesn't crush. Now, I found that actually if you do crush the core a little bit, you get a little bit of mechanical locking, and that also has really good resistance to failure. But it's generally better not to fail the core unless you're testing out and verifying that everything will work. So this is a little way to make sure. Now, once again, up here I said it was a good rule of thumb to install the fastener snug plus 1/6 of a turn. You can actually use whatever your judgment is there. However many turns you have, if it's a half of a turn, your NT is a half. If you turn it a full turn, you're going to be crushing that core, but that NT would be 1 and so on. Get that? That's how that works. This other little slide here is just letting us know sometimes it's convenient to think, well, how much axial load do I have at a given point and how much moment do I have is kind of a check. So this little slide here is taking a look at that idea. Now, what we did before, we just went straight to calculating from the moment applied what are the forces in the phase sheets. And assuming we have the forces in the phase sheets, we can figure out how much axial load do we have in the panel and how much moment do we have on the panel by just calculating that axial force per phase sheet is given by this first equation, and the moment piece, if you actually write the moment as a function of the upper phase sheet and the lower phase sheet and solve those, and if we apply beam sign convention for that, which means compression on the upper phase sheet, you can calculate that the moment, the force of the moment, that couple between the upper and lower, is given by the second equation. So the axial load can be calculated this way, and the total moment on the sandwich can be calculated this way. So that is just a little brief summary of methods to calculate the forces and moments in the core and face sheet materials when we have bolted joints in our sandwich structures. Hope you enjoyed this. Be sure to subscribe to stay tuned. Enjoy.